Hello, sir.
Hello.
Yes, sir.
Yeah, can you see the screen? Can you see my
No,
screen?
no, sir. No, sir.
Okay, so somehow this thing got turned off. So we were in this page, right? Uh, were you able to see this one, this command page?
Yes, sir.
Okay. Okay, so moving ahead, the power subsystem of a satellite. So basically, we have discussed a number of times already that uh, not only communication satellites, but also all forms of satellites, they are dependent on the solar radiation which is incident on them. Although some of the deep space planetary research satellites, I think I had shown one picture of that some of these satellites which are in deep space missions, or maybe a few are on the verge of leaving the solar system. So those satellites, they do not have access to the solar radiation that much, so they have to depend on thermonuclear generators. That means some kind of a nuclear power. They have to be nuclear powered. Although during the launch of those satellites, there is an element of risk involved. That is, if for some reason the launch mission, that the launch does not succeed, then if that satellite falls in a populated area of the world, there could be nuclear hazards, because they are basically carrying on board some nuclear based fuel for providing them with the necessary energy in while they are in deep space. Now, typically, the incident energy which is falling on a geostationary satellite, this has an intensity of nearly 1.4 kilowatt per square meter. That means 1 square meter. That means 1 square meter means something like maybe 3.5 feet by 3.5 feet. Okay. So these kind of that means over this area of roughly 3.5 feet by 3.5 feet area, nearly 1400 watts of solar radiation is incident. Now the uh, problem here is that these solar cells, they typically have a conversion efficiency of about 15 to 17% into electrical power at the beginning of their life. But you know uh, and that too gradually decreases with time because of aging of the satellite. And also there are micrometeors, very minute meteoric structures which are there in space. So when they brush or collide with this surface of the solar cells, an assembly of solar cells, they kind of damage or etch the surface. So by default, these solar cells, they have a typical conversion efficiency of only about 15 to 17%. So that means almost the whole amount of incident radiation, more than 80% of it is lost. Okay, even with so much of advancement in optical technology and other things related to optics, still we are not able to convert this incident solar energy into some kind of good percentage of electrical energy. And then because we know about the location of these stable points at geostationary orbits, they usually are located, we have seen, around 75 degree east and also around 165 degree east, the two stable points. And so all the geostationary satellites which are in orbit, they have to be, at the end of their lifetime, they have to be parked near these points so that they remain more or less confined to those locations. Because we have seen that the properties of those points are that they actually do not allow the satellites to drift away. Even if there are some forces which are acting on the satellites and trying to make them, drift away, then they will once again come back to those locations only. So that is why at the end of their lifetime, there has to be some amount of solar energy or solar cells present intact, that means in a working condition, so that the ground control segment that could actually issue command and kind of park them near one of those stable locations. Now, for performing those operations, we will need power, right? So that for that purpose, it is according to international regulations, about 15% of the uh, solar cell area has to be usually, kept intact. Are you able to see my screen?
Yes, sir.
Yes, sir.
Okay, fine. So, in case of large communication satellites, okay, they of course, because they have a lot of subsystems, large communication satellites, so they need more power to be for the internal operation. So they could generate like up to 6 kilowatt of electrical energy from the solar power if they are spin stabilized. And but however, in case of this kind of a spin stabilized circuit in a satellite, which has typically a cylindrical body covered with solar cells, we can understand that because it is spinning, so half the cells are illuminated and not illuminated at all, because the satellite itself is continuously spinning, particularly those cells which are at the edges. Okay, so what is done is that instead, if you have a 3-axis stabilized satellite which makes use of the momentum wheels, they make better use of the solar cell area. Okay, because then those solar cells, we could arrange them on flat panels, and those panels only, they could be rotated. Okay, just try to visualize this. The situation that the satellite itself is not spinning. It is stabilized using the three-axis momentum wheels. But the solar panels, which are extending out from the body of the satellite, they have solar cells present on both the surfaces. So if we keep them fixed, then only one surface of the solar cells on one surface of the panel, they will get the solar radiation and they will get charged up. But in order to maximize the output from these solar panels, if we design some kind of a mechanism so that these panels could also be rotated. Like for some time, the one of the surface is exposed to sunlight, and after some time, the panel is rotated so that the other surface gets exposed. So, sorry, in that kind of a system, what happens is that both the side or of the panel, the solar panel, that gets charged up, and depending on the orientation of the panel, we could also orient them in such a way that they are incident, because in the when it is incident, normally incident, and not at some other angle, then that results in the maximum amount of solar radiation to be absorbed and sorry, converted to corresponding electrical energy. So, in this kind of a three-axis stabilized satellite, only about one third of the total area of the solar cells is needed. If you want to do some kind of a comparative analysis, so relative to a spinning satellite, which is maintained, which is stabilized by spinning, in comparison to that, in a three-axis stabilized satellite, you only need about one third of the total area of the solar cells. And so that results in some saving on the weight of the satellite, because larger is the weight of the satellite at the time of launch, more fuel is needed. And so the cost of launching also goes up a lot. So this way, in a three-axis stabilized satellite, we could generate power in excess of maybe 10 kilowatt. Okay. Now, these solar cells, once again, as we were mentioning, that they must be rotated by an electric motor. Okay. Once, every 24 hours or so, to keep the cells exposed to the full sunlight. And this usually causes the cells to heat up, typically about 50 to 80 degrees Celsius. Okay. But in case of a spinning satellite, because the satellites, some of them are not fully illuminated, so the cells cool down when they are in the shadow and run at temperatures of around, say, 20 to 30 degrees Celsius, and they have a somewhat higher efficiency. So, during the eclipse period, to avoid, in order to avoid this requirement for large and heavy batteries, sometimes part of all of the communication systems have to be switched off. But, nowadays we cannot afford to do that, as we had mentioned. But earlier, in the 1980s, when Doordarshan was, the national program was being broadcast using the INSAT satellite. So during the eclipse period, twice a year, for about like 1.5 months or so, the national program used to be off, because the communication subsystems on board those satellites used to be turned off. But nowadays, with so much of traffic, data flowing through the satellites, communication satellites, it is not possible. There is a lot of commercial loss. Okay, you won't get the revenue if you turn off your satellite for communication capability for like 1.5 plus 1.5, so nearly 3 months in a year. It's not possible nowadays. So that is why the traffic is usually, what has to be done is you have to design either some kind of a energy efficient system, so that system is on even during the eclipse period, or if you have other options like offloading your entire data traffic for those periods. It is not a very long period, like 10 minutes to 70 minutes as we had seen. So for that period, if you can offload your entire traffic to another satellite which is not in the the shadow of the Earth at that time, so that way you can continue the operation uninterrupted, continue the operation of your communication subsystem. So a strategy which is usually followed is that if you locate your satellite about 20 degrees west of the longitude of your service area, okay, that is, you locate it in such a way, a satellite, a geostationary communication satellite is never overhead, that we know by now. So if you locate it about say 20 degree uh, away from the longitude of your service area, either side, then the eclipse will occur after 1 a.m. local time for that particular service area. So that's like in just after midnight. But even that strategy will not work for India, like countries like India or in the Far East, Southeast Asia, because bulk of the traffic, flowing from India to the US, maybe that happens around midnight. Okay, when it is daytime in the US, their offices are on. So that is why this kind of a strategy, is not very suited, very suitable for India. That is, you locate your satellite, it has to be located away from the longitude of your service area, and you can put it around 20 degree away from that longitude of the service area. But then, you cannot completely achieve this objective that there because there will be traffic even during the night time. Now, the batteries which are used on board the satellite, that means your solar energy is incident and you devise different mechanism, different strategy for converting that solar energy to electrical energy. But eventually that has to be, stored in some batteries also. So the batteries which are usually used are like nickel hydrogen type, which do not, they give out gas even when discharged to 70% of their capacity. There are, problems with other kinds of batteries where when a battery is running, that means there is no power from the mains, then the battery gradually starts to get discharged. And when it discharges to maybe sometimes 50 or 60%, then it starts giving out some gas, so which is harmful. Okay, so the advantage of using this nickel hydrogen type batteries is that uh, even when they are discharged to about 70% of their capacity, they do not gas. So that's a big advantage. And then the charging current, and I mean the power conditioning unit which controls the charging current, and kind of diverts the excess current from the solar cells. So that also has to be in a good condition. Now the typical satellite battery voltages, they range from about 20 to 50 volt, and batteries are usually rated in terms of ampere hour. That means larger is the ampere hour of a battery, more will be the amount of time that the battery will be able to provide you with a high ampere current when it is working without the mains. So that is why in case of satellite uh, communication satellite subsystems, the batteries which are used have capacities of about 20 to about 100 ampere hour. The next subsystem is one which is, the crux of the whole thing. That means this communication subsystem is eventually the heart and soul of your communication satellite, and it is the function of all the other subsystems to provide support to maintain smooth operation of this communication subsystem. So this communication satellite, basically, it's a kind of a platform in space through which you can, kind of relay your voice, video, data traffic. That is why, if you recall that Arthur C. Clarke had mentioned the satellites as some kind of an extraterrestrial relay. That means it is something which is placed away from the surface of the Earth so that it could relay your message or information to another user far away through that device, through that object in space. However, this communication subsystem, this is actually a small part. It occupies a small part of the volume, weight, or cost of the satellite in orbit. And one of the limitations that do exist, one of the major limitations, so to say, of satellite communication is that the signals that we are dealing with, they are extremely weak, and the associated power is also very weak. Okay, very small power. Because the received power in case of a large aperture Earth station, that is typically of the order of 10 to the power minus 10 watt or so. Okay, and by now, from your knowledge of electronics, you know that no electronic device or circuitry will function at that level of power, 10 to the power minus 10 watt. Okay, it is almost like noise. You have to dig out the signal from that large ambient level of noise. So that is why at one point of time, there was a emphasis on building larger and larger Earth station antennas. And people sometimes, in Germany, they went on to build one antenna which was like 100-meter diameter. 100-meter, that is like 300 and nearly 340, 350 feet diameter. Huge structure. Because from your antenna classes, I think you have already known that larger is the aperture, greater will be the gain of that particular antenna. The gain is given by an expression 4 pi effective aperture by lambda square. That effective aperture is related to the physical aperture of the antenna through a factor eta, which is known as the aperture efficiency. Okay, so that means this gain is in a way related with the physical aperture. So that was why at one point of time there was there was this understanding that we need to build larger and larger aperture antennas, larger and larger diameter antennas, in order to deal with this problem of very weak signals. But nowadays you see that attitude, that concept has changed, and we now have mobile phones very much in our pocket, as well as we have satellite signal receiving systems, which are like the size of your nail of your finger. Okay, nail of the finger, that much small in size, and they are able to track signals from satellites which are like 20,000 or 22,000 kilometers above the surface of the Earth. I think I will stop here today because this communication subsystem.
Sir,
Yes.
sir, I have a doubt regarding some of our earlier classes. Should I ask
Okay.
it now?
Yes, you can ask me here, but it would be better, if maybe we can have one separate class altogether for this doubt clearing kind
Sir,
of
it is
thing.
a very small doubt.
Okay,
Trivial.
ask me. Okay, ask me.
Sir, in case of low Earth orbiting satellites, sir,
Yes,
we had learned the orbital time period is about 1 hour 45 minutes. But
yes,
then we have also learned that the time required for one pass is about 7 to 12 minutes, as is observed from a Earth station. Sir,
yes.
shouldn't this be the same? Like, why is the time very different?
No, it is different because you try to visualize this that the low Earth orbiting satellite takes 1 hour 40 minutes or so to move once completely round Earth. And this 7 to 12 minutes, this is actually when you are trying to track that satellite from one particular point on the surface of the Earth. So that means the satellite will rise from one of your horizon and reach a sufficiently high elevation, and it will sink or set at the other horizon. So from your horizon, that satellite, from your location, that satellite will be visible as long as it is above your horizon. When it goes below your horizon, it will be visible from some other location, but not your location. So
Okay.
that interval of time when it is visible from your location, that is like 7 to 12 minutes. But the orbital period, that means the time taken by the satellite to move once completely around the orbit, that is like kind of 1 hour 40 minutes.
Okay, sir. Thank you. Thank you, sir.
Welcome. So let me have your attendance now. Okay, 301,
Present, sir.
302,
Present, sir.
303,
Present, sir.
305,
Present, sir.
306,
Present, sir.
308,
Present, sir.
309,
Present, sir.
311,
Present, sir.
313,
Present, sir.
314,
Present, sir.
315, 316, 317,
Yes, sir.
318, 319. Acha, has 318 left or what? He attended only one class. Huh? ওর নাম কি? আচ্ছা, 319 is also absent, right? 320, 321, 322, 323,
Present, sir.
401,
Present, sir.
402,
Yes, sir.
405,
Yes, sir.
what is your name?
Hello,
You were
sir.
absent in the last three classes, right?
Yes, sir.
Hello.
Sir, hello, sir.
Yes, tell me.
Sir, in previous class I was present, but I gave my attendance, but my mic was not working.
At least then some of your friends should have told me, na?
Yes, sir. I told my friends, but at that time I left the meeting, and then I know that my mic was not working.
407,
Yes, sir.
408,
Present, sir.
411, 414,
Present, sir.
420, 421,
Present, sir.
422,
Present, sir.
423, 424,
Present, sir.
Sir, sir,
yes,
420 present, sir.
430,
Yes, sir.
431,
Present, sir.
432,
Yes, sir.
433, 435, 436,
Present, sir.
437,
Present, sir.
438,
Present, sir.
439,
Yes, sir.
440,
Yes, sir.
441, 442, Shayan Datta, Ravi Kumar Thakur.
Present, sir.
Okay, thank you.
Hello, sir. 320.
Yes,
স্যার 320
320.
দেবাঙ্গনা বসাক স্যার। হ্যাঁ, আমি আনমিউট করতে ভুলে গেছিলাম স্যার আসলে।
Okay, ঠিক আছে।
থ্যাংক ইউ স্যার।